Okay, so this is the 10th lecture about energy balance. Okay, so this is the 10th lecture about energy balance, and the previous lecture I talked about efficiency of a pump and a turbine, and the purpose of this lecture is to give you an example, to solve an example with you about this issue. Okay, so this example is related to section 5-6, which is about energy analysis of steady flows. I'm still talking about steady flows. So let me go through this example, read it, and solve it with you. Okay, so what do we have here? So this example about performance of a hydraulic turbine generator. So I'm talking about hydraulic turbine generator. And so the water, let us just go through it. So the water in a large lake is to be used to generate electricity by the installation of a hydraulic turbine generator. So I have here large lake. This is a large lake, and I want to generate electricity from it. How to do this? By the installation of turbine generator, by this thing here. Okay, turbine generator system. The elevation difference between the free surfaces upstream and downstream of the dam is 50 meters. So this is, let us say this is the upstream. It's coming like this, the fluid, and going downstream. So from here to here, this distance is 50 meters, as is shown in the figure. Water is to be supplied at a rate of 5,000 kilogram per second. So the water is coming here at a rate of 5,000 kilogram per second. So I can write, I don't know, I can write here m dot is equal to 5,000 kilogram per second. It's a lot of water. If the electric power generated is measured to be 186 kilowatt, so this is what I'm getting. So this is W, let us say electricity out. So I'm getting out of this turbine generator 1,862 kilowatt, and the generator efficiency is 95%. So efficiency of the generator equal to 95%, which is same as 0.95. Okay, what is he looking for? Determine the overall efficiency of the turbine generator, the mechanical efficiency of the turbine, and the shaft power supplied by the turbine. Okay, suppose, and I will do this in the homework, I will ask you to sketch the problem. Suppose I ask you to sketch the problem. I don't expect you will sketch something like this for me. I expect you will sketch something which is, let us say, easier, more straightforward. I expect that you will do something similar to what I have told you before, okay? The one that I have showed you. So what do we have? We have, this is the generator, for example. This is the turbine, okay? And then I have, let us say, from here to here, this is the 50 meters. The fluid is coming, the water is coming this direction. So what is this? So this is the, we call it W turbine, if you remember. And this is the generator, and this is W electrical out. So W electrical out, as is given here, it is equal to 186 kilowatt, isn't it? So this is 1862 kilowatt. The efficiency of the generator, this one, the efficiency is equal to 95%. And what else I have? I have the mass flow rate, so I can write also here m dot is equal to 5,000 kilogram per second. M dot is 5,000 kilogram per second. And I believe this is all the information we have. So he is looking for the overall efficiency of the turbine generator. He is looking for the mechanical efficiency of the turbine. So just by looking at what's happening here. And he is looking for the shaft power supplied by the turbine to the generator, and he's looking for this. So This is the problem. I explained it for you. I sketched it. And now let's look at the solution. Okay, we'll go through the solution with you step by step. So the first thing to do is to calculate the, let us say, the change in the mechanical energy of the fluid. Okay, so we want to calculate. So we said, yeah, again, I can do this quickly here. So this is the turbine. So the fluid is coming from here, which is E mechanical, let us say E mechanical in, and this is E mechanical out. And we said delta E mechanical of the fluid is equal to what? E mechanical out minus N. Okay, so I can take, as he has done it here, he took E mechanical in minus E mechanical out. It is like he took the absolute value, he took the magnitude. But as you can see, he took the small e, which is got the unit of joule per kilogram. And we know what's the definition of the mechanical energy difference of the fluid. It is delta P, this is delta P over rho plus delta mechanical energy, so V, in this case Vn or V1 square minus V2 square over 2, and this is plus G Z1 minus Z2 if you want. Okay, but then what did he say? He said that Pn minus P out over rho is equal to 0. Why is that? As we said before, because the pressure here is P atmospheric, and the pressure here is, at this point, P2 is P atmospheric, so I will set this equal to 0. Again, he set V1 or Vn minus V out equal to 0. Why? Because this is a huge lake, so you can imagine it to extend all of this. So this is a huge lake, so the velocity of the drop and the level is very small. And again, this is a huge, another maybe part of the lake or the river or whatever. So the increase in the level is also very small, very minute. Okay, so we can say that V1 almost equal to 0, V2 is almost equal to 0. And here, as we said, P1 is equal to P2 is equal to P atmospheric. Okay, and the last thing, so all of those, so this is dropped, so I am left with G Zn minus Z out, which is if you remember, this was called or named delta H. So this is GH, so this is G, this is H, and I believe this is just a conversion factor. So we get then what? Delta E, if you want, mechanical of the fluid, and I can just put this in parentheses, as you can see, because I'm looking for the magnitude, and I got this magnitude when I flipped them, N minus out instead of out minus N. So I got this 0.491 kilojoules per kilogram. Okay, kilojoules per kilogram. So I can just then, if I want this, I will take whatever I got before, I will multiply it by the mass flow rate, and this is what we got here. We got 2455 kilowatt. So this is the, let us say, what I'm getting out of the fluid. This is the mechanical energy increase in the fluid. And then if I want the overall efficiency, we know that the overall efficiency is equal to this efficiency turbine generator. Okay, and as it is defined before, this is equal to W electrical out divided by the change of mechanical energy of the fluid, but the magnitude, this was given to us and this was calculated, so we got the overall efficiency to be 0.76, which means I am having 76%. This is the overall efficiency. This is the first part, part A. Part B, he's asking for, I believe, for the efficiency of the turbine generator, the efficiency of the turbine. We know this from the previous lecture, that the efficiency of turbine generator is equal to the efficiency of turbine multiplied by the efficiency of the generator. But the efficiency of the generator is given to us, and the efficiency of the turbine generator, we just calculated it here. So I can calculate the efficiency of the turbine which turned out to be 0.8 or 80%. The last thing which is required is asking for the shaft power output of the turbine, which also can be calculated easily from what we have done before, that we know that the efficiency of the turbine is equal to W shaft out divided by the magnitude of the change of the mechanical energy of the fluid. So I can just rearrange this equation. W shaft out is equal to the efficiency of the turbine times delta E mechanical of the fluid, the magnitude of it, which is equal to 0.8, which we got it from here, multiplied by 2455, which we got it from here at the top. And it seems that this is what I am getting. W shaft out, I am getting 1964 kilowatt. If I ask you to comment on this, you can comment on it as we have done always.